Hi, everybody. I guess we'll do formal introduction in a couple minutes, but I'm Evan Sherwin. Really happy to uh, be here today and talking about well, mostly greenhouse gas remote sensing, but a couple other aspects of tracking emissions. Happy to see some familiar faces on. Any questions before we start? Let's see. Um, I'll put a link. We're going to have a brainstorming Google document, and I'll just put a link to that in the chat right now. So, how was day one?
Was really interesting. I think very valuable insights, especially from the climate change perspective. For me, especially the theory and the concepts, really good.
Excellent. And so I can get a sense of the sense of the class today. Please raise your hand if your background's more on the climate change side, some field related to climate change. Excellent. And now, please raise your hand if you're in a field more related to machine learning, data science, artificial intelligence. Cool. Good. About 50-50, just as just as I had hoped. Which yeah, it's a good sign, means there's probably yeah, equal retention rates on both sides of the summer school. And to confirm, everyone who's from Climate Change AI Core team has put that in their name, just so I can keep track. I'll I'll remember you as well, but good to have. Oh, oh, good. Mine's all set on that front. All right.
Hi guys, Evan, are you good to start? Perfect. Hi everyone, I'm Preha and I'll be the MC for today's session. I'm a core team member at CCAI and just graduated from the University of Cambridge, having completed my undergrad and master's there. My research focused on foreign neural operator learning and applying it in the context of coastal flooding prediction. If you encounter any problems throughout today's session, please reach out to me via DM on Zoom or the community platform. A quick reminder that office hours today will again be held from 6 to 8 p.m. in UTC time in room 2 of Zoom. And without further ado, it is with great pleasure that I introduce to you our speaker, Dr. Evan Sherwin. I'm aware Evan will be covering his career path in his presentation, so I'll make sure to keep this introduction brief. Dr. Sherwin is a postdoc research fellow at Stanford University's Department of Energy Resources Engineering with a PhD in Engineering and Public Policy and a master's in machine learning from Carnegie Mellon University. Evan is the founder and chair of the Methane Emissions Technology Alliance International Seminar Series and a founding member on the board of directors of Climate Change AI and the program's chair of CCAI. Please join me in welcoming Evan, and Evan, the floor is yours.
And now I'm unmuted. Thank you. So it's a real pleasure to be here today. This summer school, as you know, has been the culmination of a huge amount of work by a fantastic team. And I'm really delighted to present today on the question of, well, how can we measure how we're doing in our attempts to reduce greenhouse gas emissions? So I'm, again, Evan Sherwin of Climate Change AI and Stanford University. And I'll kick things off with a bit of a discussion of this, how I got to where I am today. So I started out studying physics and applied mathematics at University of California, Berkeley. Toward the end, I realized, all right, well, okay, I want to apply what I'm doing to something that matters. And climate change really stood out to me for probably similar reasons that brought everyone here today. I wound up getting my first job at a company called Lumina Decision Systems, doing energy-related consulting, mostly for government agencies, mathematical simulation of electric power systems, vehicle transportation, looking at the potential effects of different types of policies. And I really liked it. And I realized that if I wanted to go further in this general direction, I probably needed to get a PhD. So I went to Carnegie Mellon University in the Department of Engineering and Public Policy, and got my PhD there in the Climate and Energy Decision Making Center, working with Professor Inés Azevedo. While I was there, I kept on all the projects I was working on. I kept realizing I need to learn more statistics, so I kept at it and pulled on that thread. And by the end of it, I had a master's degree in machine learning. So that thankfully left me hooked me into that crowd at Carnegie Mellon. And so when the time came for the founding of Climate Change AI, they needed somebody who knew something about carbon capture and sequestration, and so I have been involved ever since. About 3 years ago, went over to start my postdoc at Stanford University. I'll be speaking a bit about the work that I'm doing here at Stanford. I've been working with Professor Adam Brandt. It's been fantastic, and there is an awful lot going on in particularly the area of methane emissions that I think really relates to machine learning and artificial intelligence. There's a lot that can be done. So, broadly speaking, my research focuses on the role of hydrocarbon fuels in a net zero energy system. Everything I do, I view as energy and climate decision focused research. Well, all the research that I do. A good chunk of what I'll be talking about today is in the field of methane emissions, field testing of various technologies, particularly remote sensing technologies for detecting methane emissions and quantifying them, synthesizing the results of data collected with these technologies into regional estimates. I also do a fair amount of energy systems modeling. That's a lot on the optimization side, what's called techno-economic assessment, figuring out how much would this system cost if we were to build it. Machine learning, which you're all here for today, and residential energy consumption behavior research is another avenue that I've done a fair amount in. So today I'll really be focusing on methane emissions and machine learning. And so that brings us to the topic of the day. So probably everyone here's heard of the Paris Agreement. It's an agreement that was produced in 2015 at the Congress of Parties, the 21st one, to limit global warming to 2 degrees average on Celsius on average, with aim of limiting to 1.5 degrees above pre-industrial temperatures. And there's a whole lot that could be gone into on this topic. There are a lot of moving parts to the agreement, and countries are making different types of pledges to reduce their emissions and so forth. But for the purposes of this lecture on the question of measurement, I think that all we really need to go over is that countries need to have committed to peaking global emissions as soon as possible and achieving a climate neutral world by mid-century, sort of different rates by different countries depending on what they've committed to. So how do we determine whether that's happened? That's really the question that I'll be focusing on today. So we're going to begin with the first venture into the brainstorming document. Let's put that again in the chat just make sure everybody has it. So one of the goals I have for this this lecture, and I should have said it at the beginning, please feel free to interrupt with questions, especially if there's something that that isn't clear. Also, you're welcome to put questions in the directly into the Google Doc, and then we'll have a few of these sessions of 5 minutes or so where we can go into some of those questions in addition to brainstorming. But one of the main purposes of the of this talk, as I see it, is really to help you generate ideas for the projects you'll be doing in the second part of the summer school. And so to get things started, let's go to the brainstorming document and just write out some answers, or you feel free to type them in the chat if you'd prefer, or even if anyone wants to turn on their audio and video and speak, please do. So what do we need to measure to track our progress in reducing emissions? What are the greenhouse gases that matter? Well, let's start with that. And I believe I'm sharing my whole screen. Let me know if you can't see my whole screen.
We can see your slides.
Just seeing the slideshow.
Seeing the slideshow. Good. Okay. Is that better? Or yeah, I will switch over to a full screen share so that I can switch to the brainstorming document. There. Good, good, good. All right. We have gotten started. Fantastic. So this is great. So yeah, we've got carbon dioxide, methane, chlorofluorocarbons, ozone. I'm not sure what the global warming effects of ozone are, and there's ground level and stratospheric. N2O, nitrous oxide, absolutely. Aerosols, not technically a greenhouse gas, but actually can have a, depending on the type of aerosol, can have, in some cases, a cooling effect on the climate. So absolutely, that's something that's important to measure. Yeah, there's this counterintuitive effect where if by shutting down, say, coal-fired power plants that produce a lot of particulate matter and sulfur dioxide, the fact that the air is cleaner actually results in a slightly warmer climate in a bit, although on net, it's better to not have all that carbon dioxide and air pollution, which has serious health effects. Yeah, water vapor is the most powerful greenhouse gas that there is. And airplane contrails do actually have a pretty significant effect on, I believe it's mostly reflective. Sulfur, sulfur oxides are in that aerosols category. Yeah, chlorofluorocarbons. Good. So, and we've gone right ahead to sources and sinks of greenhouse gas emissions. This is amazing. So we've got certainly transportation leaks from pipelines, particularly pipelines carrying greenhouse gases such as natural gas, or methane in particular. Yep, heating, electricity generation, cattle, concrete industry as a whole. Yeah, many aspects of agriculture. Yep, wetlands, fossil fuel use, landfills, volcanoes. That's yep, for sure. That substantial carbon dioxide emissions. It's my understanding, and big aerosols, which can cool things down for a while. Beetle infestations. Yep. Those could sure cause some land biomass changes, and some sinks. Absolutely, forests, peatlands, oceans, land use change in terms of maybe afforestation, increasing the amount of biomass on land. Carbon capture can be a sink if it's taking carbon dioxide out of the atmosphere. Yep, marine plants, ice, permafrost, soils, fuel cell power plants. Fuel cell power plants probably wouldn't be a sink unless they're somehow taking carbon dioxide out of the atmosphere, but certainly it could be an important greenhouse gas mitigation strategy. Forest fires, yep. I live in California, and those are very close to my heart / top of mind a lot of the time. Subduction. I'm not sure how the movement of tectonic plates affects greenhouse gases. Good, and yeah, please feel free to continue contributing here. This is amazing. Yes, and so there's a question. Which gas has the most impact on climate change? Well, thank you for that question. That leads perfectly into the next slide. So please feel free to continue on adding here, and let's go on to answer that question. So carbon dioxide. This is a breakdown of anthropogenic greenhouse gas emissions by total global warming potential. So this is putting it all on a 100-year basis, as in how much total warming is caused over 100 years by carbon dioxide, methane, and other greenhouse gases. And these numbers are from 2015, and the 100-year basis that's often used, but that's there are different ways of doing it. But as we can see here, carbon dioxide, it's a very long-lived greenhouse gas. So on a 100-year basis, it sort of pound for pound averages out more compared to other greenhouse gases. It's anthropogenic emissions from fossil fuel use in industry are more than half on this basis. This is globally. Then land use change is very substantial. So that incorporates deforestation, wildfires, and I believe it encompasses wildfires. And then there's methane emissions, which are the second largest greenhouse gas after carbon dioxide, followed by nitrous oxide. A lot of that's from agriculture, fertilizer in particular. And then there are F gases, these chlorofluorocarbons and various other fluoride containing gases, which are, there's not a lot of them, but they have an enormous global warming potential in the thousands sometimes. So if we switch to a 20-year global warming potential, again, if we're talking about net zero emissions by mid-century, we may be talking about a time frame that's shorter than 100 years. Well, that changes the story pretty quite a bit. Methane is it's a short-lived greenhouse gas. It hangs out in the atmosphere for something like 20 years. And if we switch over to this 20-year time frame, that its contribution is relatively much larger. It's really comparable to carbon dioxide in terms of its warming over this time scale. So, and again, these numbers are from 2015, and I'm about to show you some reasons to think that the methane side might be a bit larger. So, global warming potential. I should define that. So global warming potential is the total warming induced by a greenhouse gas, total warming caused by, say, carbon dioxide or methane over some period of time. So over 100 years, this is saying integrating over the full 100, over a full 100-year time period, how much total warming does a ton of carbon dioxide contribute to the world? And similarly for methane, even though it's pretty much decayed after about 20 years, a little less, it's how much total warming does it contribute over 100 years, or for the 20-year global warming potential, how much over 20 years? And there are other methods of comparing greenhouse gases, but these are two of the most common. So, all right, so how do we actually measure our emissions, or at least estimate emissions? What's currently done by the countries that are trying to reduce emissions and document it? Well, as I categorize them, 4 basic ways. There are physics and chemistry first principles, really just going back to the basics and how we understand how the transfer of energy works across molecules. Direct measurements at all relevant facilities. That's kind of ideal in some ways, but it's not always feasible. There is emission factor estimation, which is when you don't have the ability to measure everything, but you can measure some sort of representative, hopefully, sample of what you want to estimate emissions from and scale up from that. And then there's model-based simulation using atmospheric concentration measurements, trying to back out what the fluxes of greenhouse gases are, what the emissions are. And I'll go more into these now. So physics and chemistry first principles. This one's pretty straightforward. For combustion of hydrocarbons, we've got a very good understanding of what happens when we burn methane, when we burn various different grades of coal. This is just saying, okay, what's the reaction that takes place? How many methane molecules have been burned in production of electricity or whatever the process is? Then that basically tells us what the on-site carbon dioxide emissions are going to be. So this is pretty good for electricity generation from coal, natural gas. It's pretty good for combustion emissions of oil-based products. And then there's direct measurement at all facilities, which is actually pretty much done at power plants in the United States and some other countries through what are called continuous emission monitoring systems. So these are taking samples of the flue gas that's coming out of the smokestack and measuring what's the composition. So a lot of them measure various air pollutants, but also the data are generally available for carbon dioxide emissions. So this gives us a very good sense of what carbon dioxide emissions from power plants are wherever these systems are deployed and on a lot of the time. Sometimes there are places where these systems are present but not necessarily turned on. And so this is one example of this type of approach, which can be extremely useful for just getting, we want to know what the emissions are. Well, this is what the emissions, at least direct combustion emissions, are. Emission factors are very common for more distributed sources in particular. So the basic idea is you take a small number of measurements. And I do a lot of work related to methane. So this is somebody taking measurements based on handheld devices over at an oil well. This, of course, it's a cartoon, but the basic idea is they go to a few sites, and then hopefully those sites are representative of the population as a whole that we want to estimate emissions from. And then you just scale up that small number of measurements to all the oil wells in the United States or in the world or whatever the region of interest is. And this is pretty much what's done for methane emission inventory estimates for the oil and gas sector, basically all methane emissions, including agriculture, also for a number of other areas, and for much of the world, really. So this is a really important method, but at the same time, you really got to hope that all the underlying assumptions hold up. The final method I'll talk about today is model-based simulation from atmospheric concentration measurements, or even, sometimes it's not direct concentration measurements, but estimated concentrations. So this is from a couple figures from a paper by Zheng Yuzhong, formerly who was at Harvard at the time, now at Westlake University, using satellite measurements, which are estimating. So this is from the Sentinel-5P satellite tropome instrument. And these are estimates of methane concentrations in the atmosphere above the Permian Basin in New Mexico and Texas. We'll come back to this region a little later. And what they did is they took these concentration estimates, which they're not direct measurements, but they're using the methane has is very active in certain bands of light. And so you can see based on the light that either goes through or doesn't go through the atmosphere, you get a pretty good sense of how much methane is there. And then they use a really sophisticated modeling system to back out what they estimate the fluxes to be, which involves some estimates of sort of the prior estimates of, well, what's the spatial distribution of the emissions on the ground, and what's the wind look like. There are a lot of estimates that are assumptions that go into this type of method. But one really cool thing about it is you can get an estimate of methane emissions in a place where there are no on the ground measurements at all. So all hail West Texas. Yeah, I've been out there for field work. It's one of a kind. So what are some of the assumptions that underlie these methods, and what would you say are some of the limitations? So let's go to the brainstorming document and think on this for a bit. And then also, if there are any questions about anything that's been presented so far, or just general questions, please feel free to raise those however you'd like.
There are actually a couple in the document over Q2 that came
Very
up.
good. Thank you. Okay, could plastics be considered a sink? That's, yeah. I've seen some life cycle assessment analysis. So life cycle assessment aims to estimate the net greenhouse gas emissions from some sort of a product or an industrial process. And one of my colleagues in graduate school, Daniel Posen, who's now at University of Toronto, did some work looking at, well, what are the life cycle impacts of putting plastics, or particularly bioplastics, in landfills, and sort of maybe counterintuitively, if you do the landfill right, then if you put bioplastics, the kind that you can put in the compost, into a landfill, well, then they don't really decompose in the same way, and that's actually a source of carbon sequestration that's available. So yeah, in that instance, absolutely, plastics can be considered a sink. In general, if it's plastics from petrochemicals, then the carbon atoms in the plastic came from fossil sources anyway, so they didn't come from the atmosphere. So those wouldn't be a sink, even if the carbon doesn't end up back in the atmosphere. How different are capture strategies for methane and CO2? So there are two answers to this question. One is, there's post-combustion carbon capture, or which is what people usually talk about, at least before a few years ago. That's what people would talk about when they talked about carbon capture. So that's when you've got some industrial process, such as burning hydrocarbons, that results in production of emissions. You capture those super concentrated emissions and you put them in the ground, or use the carbon dioxide for some other industrial process. There isn't really an analog for methane for that. But then more recently, there's been a huge amount of discussion of direct air capture. And direct air capture of carbon dioxide that's commercially available. There are a few companies that are working on that and have developed systems. So those capture carbon dioxide out of the atmosphere, and then you get concentrated carbon dioxide, which can be sequestered in the ground, or again, used for an industrial process. There's also a fair amount of work going on now, sort of catalyzed by some of the work that Rob Jackson at Stanford has begun on direct air capture of methane, which, because it's such a powerful greenhouse gas, even if it's capturing fewer molecules per unit air that goes through, it can still have a really substantial impact. And that generally, rather than producing a pure stream of methane, instead just catalytically reacts with the methane. It just turns the methane into something else that's not a greenhouse gas, usually carbon dioxide and water or something along those lines. So in that sense, I guess it's not even really direct air methane capture. It's more direct air methane destruction, which has the same basic effect because of the greenhouse gas potential, the global warming potential of methane so high. Is wide-scale adoption of direct air capture hindered more by the current state of technology, economics, and policy? Ooh, I don't know if that question has a straightforward answer. The technology is developing somewhat quickly, but usually technology develops more rapidly when there's more deployment. And the economics of a technology tend to get better as there's more deployment. One way to increase deployment is policy. So, yeah, I'm not sure whether there's a single answer. I think that what's the single biggest thing that could be done to improve on all three is probably deployment policy. But there's a lot of debate around around these technologies and their potential. And given how much a lot of the models rely on negative emissions technologies, I think we ought to be really looking very seriously at them So let's take a look at some of these questions, responses to question 2, or limitations of the methods. Okay, so first principles estimation. Mapping spectral information to the amount of carbon of methane. I view that more as related to regional simulation, but it's good. It's an important point. We need to know the type of coal or fuel that we're using. That's super significant because there's a methane that's that's one molecule, and that's most of what's in natural gas. But coal, huge variation in the grade of coal, like the water content, the different chemical composition, that can have a big variation in the amount of energy you get per unit, per like kilogram burned. Assuming the past is similar to the future, for basic physics and chemistry, hopefully that'll be the case. But for once you start needing other assumptions, that's really important. Universal direct measurement, hard to scale. Yep. Cheating, yeah, that's an issue. Sensors that capture all emissions. You have the sensors in the right place. It won't capture. Yes, exactly. You won't see the stuff that doesn't have a sensor on it. There could be problems with. There could be errors in the measurements. The instrument, it might be expensive. Might have a detection limit that's too high. And there's some expertise issues. Not everyone maybe is set up to use some of the technologies just yet. So then for emission factors, they're assuming emissions are basically consistent across sites and over time. It could be a lot of variation. I can tell you there is a lot of variation. Based on climate, based on all sorts of things. Spend back methods have assumptions baked in regarding emission factors. Not quite sure what spend back methods are. But additional conversions for the emission source underestimation, that's an issue. High uncertainty, that can absolutely be the case. So regional methods, it seems the models and the priors are right. That's a big question. And top-down methane estimation is based on super strongly depends on the wind. Hitting on a lot of really important points. Assumes that there's enough signal in the data to derive emissions. And the solution becomes the problem itself. E-transportation drains more power from the power plant. There are questions of the life cycle emissions of electric vehicles and all the rest. So important questions there. Very good. So let's see. Any more? Good. A couple more questions. What about combining different methods? Oh, absolutely. That is a fantastic approach. I could even link to a talk by Daniel Cussworth at my Methane Emissions Technology Alliance webinar series, which does exactly that. I think that's really necessary. And a question of how much does home energy and gas play a role, especially since that's likely not to be measured? Well, so the home energy consumption is measured pretty well just through customer meters. Usually, it depends on the country. Leakage of gas in households, there's some uncertainty there. It's so on the leakage side, that's certainly something that matters and needs further investigation. Most methane emissions are at the production site or in sort of what's called midstream of getting the gas from production to where it's going to be consumed. And research on climate change should tackle all the existing processes in other fields. There's so much to do. How does the cycle stop? I mean, it stops when we get to net zero emissions. There's a huge amount of work to do. So what's industry for fossil fuel emissions? So this can be something like cement manufacturing or fertilizer production. So this is not electricity generation, which is a significant fraction of particularly carbon dioxide emissions, but emissions for steel smelting, a bunch of processes that produce a fair amount of greenhouse gas emissions, but for production of various goods.
Hey,
And,
Evan.
yeah.
This is my question. Can I ask one more question to follow up?
Sure. Yes, please.
So that would be like, literally when you're constructing the material of concrete, things are emitted that emit greenhouse gases. And it's not like, oh, you need to, run some motor that would make the concrete better and then the motor would emit emissions. It's actually like the process itself or whatever that sort of, okay, cool.
Yeah, concrete actually, one of the typical processes for producing it tends to make a pretty high concentration stream of carbon dioxide, which could be, if we want to do post sort of process carbon capture, something like that's a pretty good way to start.
Cool. Thank you.
You're welcome. Cool. Well, this is wonderful. And yeah, let's go back to the presentation, but we will come back to the brainstorming doc. And yeah, how are we doing on how long are these brainstorming sessions turning out to be? I budgeted 5 minutes, but there's some slack in the schedule too. Maybe if we can put that in the chat. 10 minutes left till the break. Cool. All right. So which methods do we use for which sources? This is a figure from the Global Carbon Project, which catalogs all the sources and sinks of carbon dioxide, methane, and other greenhouse gases. And in my view, we've got a pretty good understanding of carbon dioxide flows. Well, not to say that there's definitely substantial room for improvement, but the estimates of the Global Carbon Project in terms of fluxes are, well, yeah, quite a lot from fossil fuel use, and I believe that includes industry. Sort of modest uncertainty there compared to the total land use change. That's a substantial source, and the relative uncertainty is a bit higher than land uptake. So this is biomass production and various other ways in which carbon dioxide is pulled out of the atmosphere. Again, there's some uncertainty here. And oceans are a major sink of greenhouse gases. And then there's this is the atmospheric increase, which is way too high. So yeah, there's some uncertainty here, absolutely. But we also, even if there's not a continuous emission monitoring system on a power plant, we can the flows of fuels such as coal, natural gas, oil, those are tracked pretty well. So we know how much is going into a country usually. We know the grade pretty well. We can usually get a pretty good estimate of emissions from just based on the fuels that are going into a country, of combustion emissions. That's key, not upstream methane emissions. So for methane, there's a lot more uncertainty. Here, this is also from the Global Carbon Project. Here are the anthropogenic emissions on the left. So fossil fuel production and use, it's ballpark a quarter of human-made emissions. Then there's agriculture and waste, which is even larger. So that's cattle farming, landfills, and quite a few other sources decomposing of agricultural residues. There's biomass and biofuel burning, which is kind of listed as a combined natural and human source. And then here are the natural sources and mainly sinks. So we've got wetlands, or this is a source, and some other emissions from things like termites and other various sources, permafrost, and all that. Maybe a much larger one in the future. We'll see. Big sinks in the atmosphere, and some sinks in the soils. So we see these numbers. There are two sets of numbers for every estimate here. So they're the bottom up estimates, which are, again, that's based on scaling up from a small number of measurements generally. And then there's the top down, that's basically those regional simulation methods based on concentration measurements. And there's a lot of uncertainty here. We see for methane emissions from fossil fuel production and use, the smallest number here is 81. And then these are all in million metric tons per year, teragrams per year of methane. And the biggest number here is 154. So that's a factor of almost 2 in uncertainty. And the rest of the numbers, they're not all that quite that much uncertainty, but there's a fair amount. There's a lot we don't know. And so I'll be focusing a lot on, before we go there, for F gases, I guess I didn't include nitrous oxide here. There's a lot that needs to be done there as well, but I'm less familiar with the agricultural side. For F gases, frankly, there's a lot we don't know. Many air conditioner units, heat pumps, which are becoming a bigger source of home heating, refrigerators use F gases as the refrigerant. And right now we're basically just hoping that when these appliances reach the end of life, they are properly recycled and the F gases are either recycled or destroyed. There's some signs that might not be happening as frequently as we want, and we really need to get a clearer handle on what's actually happening here. So this is a big open area that I think needs more research. So as a recap, what methods do we use and where? We've got this is just a subset of sources. Of course, there are many more sources as you listed in the brainstorming doc. So for carbon dioxide from power plants, we can use first principles. In some countries, there's universal direct measurement with continuous emissions monitoring systems. Emissions factors we use in some instances, and I haven't really seen regional simulation used for power plants, although I'm sure you could do it. Then there's oil and gas facilities. If we're looking at the methane emissions from oil and gas, first principles is more difficult to apply because how much is leaking? Well, physics and chemistry can't really tell us that. Engineering kind of can. So to the extent that in a process simulation for a pneumatic compressor that is built to emit some methane, and some of them are just by the way that they're designed, maybe that counts. So universal direct measurement, we're now in a world where that's something that really can be done, not all the time, not continuously, but we can, with remote sensing, measure pretty much every oil and gas asset in a region over a pretty short period of time. Emission factors are probably the most common method here. And then there's regional simulation, which is quite common as well. And for wetlands, forests, both carbon dioxide and methane, really from both of them, they're not point sources. It's the best we can generally do is emission factors or regional simulation, at least right now. And maybe we'll set up a giant emissions monitoring system in the wetlands and forests. Who knows? And then for for air conditioners, well, we're in my view, we're in pretty rough shape. So now we're gonna go into the question of how can machine learning AI help? And this is a recap from the intro to machine learning slides. And I know that we should go to a break in a minute. Who can? Okay, so this is, I like this cartoon of what machine learning is. You take inputs and outputs, and then you create a program. You develop a program, or really the algorithm that you put in develops a program on the basis of the inputs and the outputs. So this is something to keep in mind as we go to the next part. So I guess now let's do a break, and let's do a 10-minute break, and then maybe within that, feel free to populate this document if you want, but feel free to take the full 10-minute break. And I'll yeah, see you in 10 minutes. Hey, everybody. We'll give a minute or so. Oh, please, Korea.
Oh no, sorry, I was just turning my video on.
Cool. Well, yeah, shall we keep on going, or should we give another minute? All right, let's do it. Cool. So yeah, this is wonderful. So we've got a bunch of yeah, ideas of how AI can help improve greenhouse gas measurement. So here, yeah, machine learning on satellite data to estimate greenhouse gas emissions, carbon stocks. This is a huge area. We'll be talking about more about this in just a few minutes. Machine learning tools to ensure most exact measurements. Learning accurate emissions from atmospheric measurements, physical as a physical basis, with a physical basis as ground truth. Yeah, we'll be talking about ground truthing, remote sensing in a bit. Interpolation when measurement sites are sparse. This is huge. And we'll talk about this in the context of wetlands, but there's a lot to be done here. Monitoring and identifying unreported activities. Oh, there's a great paper that I didn't include in this presentation on counting cows in the Amazon to track illegal deforestation for cattle farming. There's really a lot to be done here, just in remote sensing in general, for finding things that we didn't know were there. Machine learning to process satellite data, yes. Tracking land use, detecting methane hotspots or hotspots of other greenhouse gases. Identifying areas where there's potential for increasing the use of solar energy. Yeah, definitely. The question of where good places to put solar are really, there are a lot of factors there. It's not just how much sunlight comes in, what about the clouds and the seasonality of it. Educating stakeholders on the concepts of machine learning and how to deploy explainable and reproducible models for their factories and transportation. Yeah, so there's quite a lot that can be done. I mean, not even just for measurement, but for actual reduction of greenhouse gases. And there are great examples of this from, say, Google with their data centers has deployed machine learning to reduce their energy use for cooling quite a lot. So the more stakeholders understand what's really available, what can be done, the more can be done. And monitoring the impacts of greenhouse gas emission reduction interventions. Yes, this is a big area. If we've got data that somehow can tell us what the impact has been, and we know where an intervention has happened, then machine learning. Well, interesting. So yeah, monitoring an impact, that's usually a causal question, and depends on your definition of machine learning. But there absolutely are types of machine learning that can tell us not just predict what's going to happen, but say what happened because of something else that happened. Develop deep learning models to detect anomalies. with respect to nations and, and sue them at the UN. I'm not sure what the legal framework is around emissions anomalies, but certainly we could detect anomalies using machine learning in a few different ways. And tracking policies with not natural language processing. Yes, absolutely. And there's going to be the tutorial later today will be focusing on some aspects of this. And it seems like there are a few more questions. I'll go through quickly. So yeah, so from the graph and the bullet points, yeah, physical and chemistry, tracking of combustion emissions. I'd say that's quite accurate if the chemical characteristics of the fuel being used are well understood, and as long as there's not like crazy incomplete combustion going on in the plants. The blue part of the graph, yeah, I can go back to that graph. That's an important point. So yeah, so the goal is to get this blue part to not exist. If we want to get to net zero emissions, that's what that means, that there's no imbalance, that all the sources and sinks of greenhouse gas emissions are balanced. So there's a question about how accurate do we need to be? This is depends on the application, but there's I'd be really happy if we could get 5% accuracy with a lot of these estimates. Yeah, what are the greenhouse gases, the F gases? So yeah, fluorinated gases. There are a bunch. Yeah, most of them are refrigerants. There are some others that are used in different industrial or other processes. Air conditioners are a big, big source. I'm not sure what the biggest source of F gases is. Do heat pumps? Depending on the type of heat pump, a lot of them do use F gases as refrigerants, but there are, I believe, models that don't. The spend-based methods, I think, for the clarification on this is a question of emissions accounting based on sort of expenditures of a company and estimating emissions based on that. Yeah, big policies for reducing greenhouse gas emissions. Maybe affecting the price of goods. So how do we balance reducing greenhouse gas emissions with purchasing power? I think in not all instances is it a question of either or. There are quite a few cases where, for example, wind and solar energy on just a per unit energy basis are some of the cheapest sources of electricity that there are. There's quite a lot that can be done to reduce emissions that I don't think would really reduce purchasing power at all. That said, if we really want to completely turn over the energy system to something that's net zero emissions in a short amount of time, in the short run, yeah, this might have some effects. And this question is not one I can answer in a couple minutes, or really one that I think has a super straightforward answer. Question on accuracy of measurement. Isn't what we need for directionality and triggering behavior change, rather than aiming for super accurate estimates, not being able to trigger related action. Yeah, so the question is basically, does it matter that much if we're super accurate, as long as the information is being presented in a way that results in emission reductions? And I think in some contexts that's probably, in some contexts that's probably a reasonable approach. At the same time, if we want to commit to net zero emissions, that we really, in my view, do need to have some pretty good measurements to make sure that we know how far we are on that path. So yeah, next let's go. All right, so again, we've got this recap of what machine learning is, and so keep this in mind. What's the input? What's the output? What's the program? So I'll be speaking a fair amount about remote sensing next. A lot of our estimates that we're using now of greenhouse gas emissions are based on, somewhat based on measurements, but there's a fair amount of error in those estimates. We don't we don't even know where a lot of things that emit greenhouse gas emissions are. So that makes it really hard to track. We don't, even when we do know where the location is, we may not know what kind of equipment is present. And the type of equipment can be a huge determinant of emissions. It's, if we want to take ground-based measurements of everything that could emit greenhouse gas emissions, that could take a really long time. And satellites are pretty amazing. They can see just about everywhere on Earth as long as it's not cloudy, and airplanes can see. I mean, as long as you get permission to fly, you can see even more. So in remote sensing, what is remote sensing? Remote sensing is seeing things that are seeing things from far away, basically. So here's an example from a workshop paper from our 2020 Neural Information Processing Tackling Climate Change with Machine Learning workshop that's aiming to track emissions from every power plant on Earth using satellite data. So this is a satellite image of a power plant, and we can see here that they can see the smokestacks, and from the cooling towers they can see, well, okay, there's a lot of steam coming out today, or out of this one there's not much steam coming out, and that can give a pretty good sense of what of how much electricity is being produced, especially if one understands what the efficiency of the power plant is, and some information about the cooling system. But even without that, you can get a pretty good guess. And this, obviously, in a case, if we had a continuous emission monitoring system, we wouldn't need this, but we don't have those everywhere. So this, well, so what's the input here? What's the input to this machine learning model? Feel free to just speak up or post in the chat or in the Google Doc. What's the input to this model? Yep. Oh, thank you for posting. Yeah, the input is so we've got a response of pixels, and basically, yeah. So the input is the images, is the pictures of from the satellite. There's a question of how do we differentiate between a coal-fired power plant and a nuclear power plant? That's a super important point. If we don't know what the fuel is for a power plant, we wouldn't necessarily be able to tell. So it's good to have some basic information of this is a coal-fired power plant or a natural gas-fired power plant or a nuclear power plant, because of course nuclear wouldn't have any direct on-site emissions. And so what's the output that this machine learning model is? We're putting in inputs and outputs, and we're getting a model, getting a program. What's the output that this model is being trained on? Yeah, output of the power plant, exactly. So the model is to train this. We initially have some input images of power plants at various levels of generation. We've got some training data that have the actual power output. So maybe we train it in the United States, where we have these continuous emissions monitoring systems, and so we've got the greenhouse gas emissions, we've got the power output also, and we can then see how we can then plug that all into a deep neural network. I won't go into how that works today, but that'll basically learn some patterns, and then we'll be able to just put in some of these images and get estimates of the total emissions from a given that are represented in a given image. And of course, it's more complicated than that, but that's the basics of it. Yeah, how reliable? Yep, wind speed. Ooh, all right. We're gonna get to the question of wind speed soon. That's super important. How do we differentiate between white smoke and power plants and clouds? Yeah, these are all. Yeah, again, it may be a somewhat simple concept, but it's in practice there's a lot of difficulty. who's training, what's the training data, images. Yeah, exactly. The training data is images of power plants where we've got some sort of measurement of the emissions. And it looks like it also uses, oh yeah, awesome. That's a really good point. So it's not just using visible images, it's also using infrared images, so that can tell you what's going on with heat, which is super important information. Yeah, how transferable are these models from one region to another? That's that question has a lot of different answers depending on the model and the regions. And good. So yeah, so this is one example where machine learning can really help track greenhouse gas emissions. I'll be talking next about methane. This is a topic very close to my heart. I've been it's most of what I've been doing over the past 3 years. So methane, it's not you can't see it with your eye, but it is being emitted in many instances. So this is an oil well cartoon. It's got methane emissions. Historically, the way we've found methane is through handheld devices of various sorts. But again, that's pretty labor intensive. Over the past 10 years or so, vehicle-based methods that have a methane concentration meter or another device for measuring methane have become more popular, especially in the scientific literature. And then continuous emission monitoring systems where you just have something on site that measures methane. Those have, in the past, I'd say 5 years, really started to become much more popular. But I'll be focusing today on remote sensing from aircraft and satellites. So there are a few ways of doing it, but basically, again, methane is precisely because it's a greenhouse gas. It's very active in terms of absorption and emission of certain frequencies of light. So if you look at the different frequencies in sunlight that has gone through methane or has not gone through methane, then you can get a pretty good sense of how much methane is there. And there also are active systems that shoot lasers down that are super cool. But I'm going to be talking about the reflected sunlight systems mostly today. So this, in the past couple of years, we've really seen a lot of results from these methane remote sensing systems. This is an image from the Dan Cusworth and others, the Carbon Mapper group. This is an aerial image, and some of these methane plumes are like a couple kilometers long. So those are big. This is in the Permian Basin, same region as before in Texas and New Mexico. And then here, this is using that Sentinel-5P tropomy instrument, the same one that generated those concentration maps before. And it covers the whole world every day. It's got pretty low resolution. It can't see small point sources, but it can see things that are like 10 tons or bigger of methane per hour. 10 tons methane per hour is a lot, and there are quite a few emissions that are even getting up to more than 150 tons per hour all over the world. So this is really concerning. And so yeah, there's clearly a lot of room for a lot of room for us to learn here. A few notes on remote sensing of greenhouse gases. Remote sensing, I should say, of individual carbon dioxide emissions can be done, but the source needs to be quite large. So I've seen some aircraft-based estimates of point source carbon dioxide emissions. I haven't seen a lot of satellite-based. F-gases, also I've seen some aircraft-based F-gas sensing, but thankfully, usually the emissions are not big enough for a satellite to see. And nitrous oxide emissions from, say, fertilizer, super diffuse, hard to measure directly with a point source, at least. There aren't that many point sources. Hard to measure with satellites, although you probably, I haven't seen a lot on the regional methods. My guess is that would be the way to go, the more regional estimation. And we've got some questions coming in. Does atmospheric methane have public health implications? apart from climate change, not really. It's not like breathing methane. It's not a huge hazard. It's explosive limit. There's a pretty narrow range of concentrations in which it's explosive. So thankfully, that's the one less thing to worry about as much. So to give a sense of what remote sensing is telling us, this is from a study with an excellent PhD student led by Yuanlei Chen, who I work with very closely. And this takes hyperspectral, this aircraft-based method. So essentially, our partners, Kairos Aerospace, flew over the entire New Mexico Permian Basin, at least the oil-producing part, and found a lot of emissions. So this is this part of New Mexico, and this is what these emissions look like in their system over. This is an oil well, and what we found here is that the emissions that we're estimating, so just what we measured, that already is much larger than the existing government estimates of methane emissions, which are using these emission factor-based methods. And then if we extrapolate to the emissions below what the airplane can see, and to account for the assets we didn't cover, that brings us to about 6 times this the estimate from the bottom up. This emission factor-based method that's used commonly, that's by the Environmental Protection Agency in the United States, and basically these emission factors are used by most countries that don't generate their own, which is quite a few countries. So it's not just a US question. There's a very good chance that methane emissions are probably not underestimated by as much as they are in this particular region. There's a lot of reasons to believe that this is a particularly high emitting, at least at this time, was a particularly high emitting region, but it's a cause for concern. So how do we know whether these methods work? One of the things I've been able to do over the past few years is controlled methane release testing, to just ground truth methane remote sensing methods. So we've tested out at this point several aircraft, a bunch of satellites, and this is us out about a year ago in the desert in Arizona with a big trailer full of liquefied natural gas, heating it up to more or less ambient temperature, and then releasing it through this big stack at the end of a truck bed. This is the team. This is Adam Brandt, my mentor, Jeff Rutherford, who just the second from the left, who I've been working very closely with, another excellent PhD student finishing his PhD soon. Then Tyler Farmer Mullen on the left, one of the technicians who just we cannot express our gratitude enough. So what did we find? So I'll show some of the results from the satellite testing. We're doing a single blind test where we're on the ground, we're releasing some metered amount of methane, we know how much we're releasing, and we're communicating nothing to the satellites other than roughly where we are and that we will be conducting a test. We're also measuring wind speed. That'll be important in a minute. So how'd they do? Pretty well, in my view. So we gave everyone about a 4 ton per hour emission, plus or minus half a ton. And so these are all the satellites we tested. These 4, and then this GHG sat. They did their own. And these are the teams that analyzed the data. So in many cases, multiple teams analyzed the same spectral data, the same data from the satellite. We see that the numbers here, there's some uncertainty, and if you want to dig into the uncertainty on all these bounds on all these numbers, then it's all in the paper, which is up on Earth Archive, the preprint. But yeah, these are looking pretty good. We can see there's a lot of variation in even what the emission looks like based on the method. Even though these emissions are about the same size, for some of these satellites are a little less sensitive, but cover the whole world in a period of timescale of about 2 weeks. And then some of these more targeted satellites down here you can see they're much more sensitive. You can see that they can see more of the methane that's sort of around. And I could talk about this figure for probably too long. So, but the main takeaway here is that it looks like these methods work quite well. And I'm going to dig into this figure right here from this company called Kairos, which is analyzing data from many different satellites to detect methane emissions, among other things, to highlight a question that's super relevant for machine learning, which is, what's actually a methane emission? So before they applied their algorithm for determining what's a methane plume and what's not, you can see that there are, in the raw spectral data, if they just do some simple differencing of the relevant spectral bands, then you can, this area, which is sort of agricultural and residential, it looks kind of like there's a methane enhancement there, even though there wasn't. So there's a lot that can be done to filter out the background, and but there also is a decent amount of manual checking in the way that things are often done now. I'm not sure of every system's every group's process, but if we being able to determine really accurately what's an emission and what's not an emission, that's something that, if we've got good ground truth, can be a really impactful application of machine learning. Because even if we have a 1% false positive rate, well, if we've got satellites circling the entire globe multiple times a day, a 1% chance that a given image is going to have say there's an emission when there's not one, is going to mean there will be way more false flags than false positive emissions than there actually are emissions identified. So this is an important question, and I think really there's a lot of room for impactful work here. Oh man, cool! A lot of great questions coming in that I will get to in the next break. And to highlight this again, this is work by another student I work with, Jan Zhang. I'm so lucky to work with such fantastic students. This is applying one of the standard methods for methane retrieval to the same site that we did, but on a day when we weren't emitting any methane. And this method found, it said it found some methane, but we're quite confident there wasn't any. So these methods certainly can produce false positives if one isn't careful, which means that this, which really highlights the significance of developing methods that ideally can just automatically process and reliably process incoming data to find the emissions that we've seen from some of the previous slides. There are quite a few big things that satellites can see. So to this question of wind speed, which was raised earlier, it's essential. So this is a cartoon, but this is a methane emission coming from an oil well, and this is wind blowing at a given speed. Well, if we have an emission that's twice as high with twice the wind speed, these two basically look identical to most remote sensing methods. So if we want accurate quantification of emissions, it's really helpful to have accurate wind speed information. Unfortunately, in most cases, we don't have direct on-the-ground measurements of wind speed, and even there's a lot of variability in what the wind's doing at 5 meters, 10 meters, 20 meters. But usually all we have is what are called wind reanalysis products, which are model-based estimates of wind speed. They tend to be unbiased on average, usually in most places, but there's a fair amount of variability there that they can be off by a factor of 2, 3, sometimes even. So this is if the wind speed's off by a factor of 2, then well, so is the quantification pretty much. And so one way that that AI, that machine learning can help with greenhouse gas remote sensing is by removing wind speed as a factor. So yeah, the wind speed estimates we have are usually pretty noisy. What if we could just train a model to estimate emissions based on the shape of a methane plume? That's what a group at Caltech is working on right now, Caltech and NASA Jet Propulsion Laboratory. They're just taking in the raw emission sort of image, looking at the shape of it, and just feeding in the pixels basically, and they've got the true values. These are, I believe, based on simulation so far, but hopefully will be applied to ground truth, like metered controlled releases soon. And it's looking pretty good so far. There's more work to be done, but this is an area, if we could get reliable estimates that just didn't need wind speed, that would be enormous. And how am I doing on time? I am at, good. I think I'm doing okay. Another area, remote infrastructure mapping. Again, we just don't know where all the landfills are, all the oil gas facilities. These are a few different papers, all the dairies where cattle are. There's a huge amount that can be done here. These are a number of papers, two from our 2020 Tackling Climate Change with Machine Learning workshop, finding oil and gas, oil import-export terminals, processing plants, wells, and even finding the number of tanks that are on a well site, which is super relevant to estimating total emissions. And then down here, this is the estimating, is finding facilities that house cattle. And if we can find where all the places that the cattle are, then we can estimate the methane emissions, still using emission factors, but there hasn't been a census of cattle in quite a while in a number of regions. So this type of method can be really useful. And yeah, filling in missing data. This is work that by Jeremy Irvin and others. We all know Jeremy, taking measurement tower data from wetlands. This just wonderful network of towers that measure atmospheric concentration of methane and various other gases, as well as wind speed. And these this tower network gives us some information about methane emissions from wetlands, which is a fair fraction of total emissions. But of course, there are a lot more wetlands than there are towers, so we want to be able to scale up from these tower measurements. But before we do that, we want to make sure that in order to collect a valid measurement, atmospheric conditions have to be just right. So there's a fair amount of missing data. And well, what if the missing data is correlated with the methane emissions at that time? Then that could produce biased estimates if we don't correct for that. So that's this question of finding an unbiased way of filling in missing data for these towers, so that we can then produce scaled up regional and global estimates of wetland methane emissions. That is what Jeremy and his collaborators have done. And yeah, so there's a lot of room for improvement. That's one thing I really want as a takeaway from this talk. There's quite a lot that could be done to make emissions tracking better. There are a lot of sources that we need to estimate emissions for. We don't know where a lot of them are. A lot of methods that we use right now rely on pretty small data sets and are pretty have assumptions that are. It'd be nice to have a stronger foundation for. One thing we didn't really talk about is, well, what if what if there's bias in the measurement used for collecting emission factors? Well, that would bias everything down, and that's probably happened in some cases. In many instances, yeah, the measurement technology is just getting better, and there's a lot we can learn just from deploying some of these new technologies, particularly in methane sensing, but also elsewhere. Yeah, remote sensing can just help us find out where things are can help us find emissions where they're occurring. And machine learning can help us fill in a lot of the gaps in data and a lot of the databases we have. So with that, I'd like to conclude with with some thoughts on what who are we producing these better estimates and better ways of tracking emissions for, and what do they need? But I imagine there's a fair amount coming up in the doc. So yeah, let's open this up to Q&A, and we can just do these last two questions at once because we're pretty close to time. So who are the relevant stakeholders? What do they need? And what AI projects would help these stakeholders the most? I mean, if you think of a great one that you want to be your project, you're also welcome to just keep that as to show us all in a week. But so let's see. So what sorts of questions are coming up? So how do we do coal versus nuclear? Talked about that a bit. How reliable is the estimate of plume size? So the question of what is the size of a greenhouse gas plume is kind of a philosophical one, because of course it tails off, and some instruments would be able to see one fraction of it. More sensitive instruments will see a larger amount of it, and it's a question that doesn't have sort of a general answer. As far as the question of with a given sensor, it does. With a given sensor, we can say with this satellite, a methane emission of this magnitude at a given wind speed is going to look 20 meters across or something like that. But yes, wind speed is critical. It's basically proportional. We need our estimates of both the length of the emission, of the magnitude of the emission are pretty much directly proportional to wind speed. Could the model be used for other images? Which model? That's a question of transfer learning, and in some cases, models can be translated into other applications, maybe with a little additional training. There's a lot of work in what's called foundation modeling that are sort of these big overarching, usually image recognition, but sometimes other things, models that can be repurposed quite easily for specific tasks. Can we use hyperspectral images? Yeah. A lot of this methane sensing uses hyperspectral imagery. So what hyperspectral means, just basically a lot of different frequencies of light at usually pretty high resolution. And that can be very helpful, because a lot of methane sensing, a lot of greenhouse gas sensing is based on differences in the prevalence of different frequencies of light. And the more frequencies of light you're looking at, the easier it is to pick out exactly what you're looking for. Are there really no methane sources over Europe? Hard to say. So Europe is there's not much production of oil and gas in Europe, at least onshore. But offshore it's a lot harder to detect with satellites. There are ways to do it with what's called glint. If the sun's at like just the right angle and the satellite's in just the right place, there's some really cool work that's been done in that area. But in general, it's really hard to see. Another factor is clouds. Much of Europe is pretty cloudy, which makes it harder to just see whether emissions are there or not, because most of these remote sensing methods just can't see through clouds. So I can't say for sure there are no big methane sources over Europe. And again, these are like 10 tons of methane per hour or more. There certainly are methane sources smaller than that, but it is possible that there weren't any in that magnitude during that study period over Europe. Sinks of nitrogen gases. I need to learn more about nitrogen, nitrous oxides, and really the nitrogen cycle. So I don't have a great answer for that question. My guess is yes, Or oh yeah, of course there are sinks for that. Nitrogen fixing, and that's what peanuts are good for nitrogen fixing in the soil. So yes, there are sinks of nitrogen gases. I'm not sure if there are sinks of nitrous oxides. Is there any realistic ongoing work for more precise satellites for methane detection than Sentinel-5? Yes, absolutely. So all the satellites that that I showed in the controlled methane release test, those are all substantially more sensitive than Sentinel-5P. So the most sensitive is the satellite that saw the smallest emission. There are two we tested that might have been able to see this. GHGSat saw 200 kilograms per hour, and we that's the smallest thing we gave them. We're going to be doing another test in a little over a month, and hopefully we'll have a chance to test out, really get a clearer picture of that minimum detection range. Worldview 3 is claiming similar accuracy, so we're going to test that too. And the Sentinel-5P or Sentinel-2 and Landsat 8, those both saw emissions down to the thousands of kilograms per hour, and in the case of Sentinel-5P, down to about 1.5 tons per hour. Did I say kilograms per hour before? Thousands of kilograms. That's correct. Then the Carbon Mapper satellites are scheduled to launch. Those will be comparable to the GHGSat satellites in their sensitivity. There's a bunch going on in this space, and it's a really exciting time. The Environmental Defense Fund's methane sat should be launching in the next couple of years. We tested their aircraft version, and those results should be hopefully published before too long. Are only pixels fed into the model? Is there other information that could be used as an input? Definitely. So there is, if we wanted to do this power plant emission estimation, if we have some information about the efficiency of a power plant, then that can be really helpful. If we know about the cooling system, that's all information that can be fed into a model. If we know the characteristics of the fuel, what's the amount of energy per kilogram of fuel going in, which there's a lot of variation for especially for coal-fired power plants. Those are all very useful inputs that could be added. What kinds of building standards are such kinds of building standards in how they appear in satellite images around the world? Yeah, regional variations in building standards and how buildings look. Yeah, absolutely. There's a lot of variation in how buildings look. I realize we're actually, I guess, technically ending in 3 minutes, but I want to take a look at some of the. So yeah, who are the stakeholders? These are wonderful answers. Some AI projects that would help these stakeholders the most. Again, feel free to show us in a week what you're thinking of, but also feel free to write any out here that you think would be cool. All right, so quite a lot. Let's see, any burning questions? Any burning questions for the last 3 minutes? There's one here. What are my thoughts on the cost of generating ground truth labels for satellite data, both for segmenting plumes, buildings, other things, in terms of time spent labeling, cost of employing people to do so? Will this scale to larger regions? Do we need AI approaches? Yeah, I think it's generating ground truth labels. It may be a less glamorous task than training a fancy model, but it's absolutely critical. The cost of generating ground truth labels for these methane sensing satellites was at each of those data points, depending on how you count, but was thousands of dollars to just have all that stuff out there. But if we hadn't done that, we would have no, we wouldn't really know how well these technologies worked. And these are going to be used for all sorts of policy applications. Companies are going to be making big decisions based on them. So I think it's really worthwhile to generate ground truth validation. Absolutely, for buildings and for other features we might just be finding on the ground. Yeah, there's a lot that can be done just by human labeling. In some cases, it might be necessary to send a person out, see what's going on there, or dig through government records. And it really depends on the application, because it doesn't matter how fancy the model is. If the input data doesn't have good ground truth information, then there are going to be real limitations to the model. Equity implications of these emissions locations. Yeah, how to study the equity? Well, a big equity implication of emissions is, even though methane's not a health damaging air pollutant, I know that we're at time technically, but I'll go a few minutes over if that's okay. But of course, feel free to sign off if you got to go. There are usually emissions of volatile organic compounds and other health damaging air pollutants together with emissions of methane. So if those are close to population centers, that can be a real concern for human health. Oh yeah, did it hurt my soul a little bit to release all that methane? Having seen what's happening in the Permian Basin, I have not at all. We need to really reliably understand how these technologies work, and if there's doubt over what these technologies are seeing in the first place, then their impact is going to be limited. So I really, obviously we were very careful with the emissions we released, and didn't release anything we didn't need to. But no, I'm really proud of the work that we've done. Oh, I need to show. I realize that I haven't shown acknowledgements. I should acknowledge my wonderful collaborators, my funders here, and I believe the slides will be shared. Human methane emissions rather than cattle. So cattle emit methane because of their digestion. Cows have 4 stomachs, and they are digesting grass and hay and these super difficult things to break down. And because of what's going on in their gut, that produces methane. They burp it out. Humans don't really produce methane through digestion in the same way. So thankfully, that's one less thing to worry about. Yeah. So let's see. Any other burning questions, or if not, we can call it a day. Cool. Well, thank you so much, everybody. This has been an absolute blast, and I hope that the rest of the summer school is. I look forward to seeing what you develop in the next couple weeks.